In this video, we shall look at a few review problems on electric flux and Gauss's law. First, a brief introduction. How do we calculate electric flux? Electric flux is represented usually by this symbol. And if the electric field is uniform, then the associated electric flux is calculated using a dot product of two vectors. The first vector is the electric field, and the second vector is the area vector A. How do we represent this on diagram? Assume we have a plane like that. The normal vector to this plane is heading that way. Let's call it n hat. The area of this plane is a meter squared. So the area vector is defined as A times the normal vector, n hat. Now let's assume you have electric field penetrating this plane or this surface, and this electric field makes certain amount of angle, say alpha with respect to the normal vector of the plane. Then this expression gives electric flux due to this electric field through this area A. It's usual that we introduce a subscript E to denote that we are talking about electric flux. And using the expression for dot product of two vectors, the electric flux can also be written in terms of alpha in the following manner. It is just the magnitude of the electric field times the area of that plane times cosine of alpha, which is cosine of the angle between the electric field and the normal vector to the plane. The SI unit to measure the electric flux is simply Newton per Coulomb meter squared. Now we know a little bit about electric flux. Let's look at Gauss's law. Let's assume you have a spherical surface like that with a radius r. Within this spherical surface, assume you have two charges. One charge is plus 2q, the other one is minus q. Then we should anticipate electric field going outward through this spherical surface, like that. It's outward because the net charge is positive. Gauss's law says the electric flux through such a surface, such a closed surface that is, equals the net charge enclosed by the surface over epsilon naught, where epsilon naught is the permittivity of vacuum, and its value is given by 8.85 times 10 to the power minus 12 in SI units. Such a closed surface is known as the Gaussian surface. It need not be a spherical surface. It can just be, for example, a cube or any other closed surface within which you have the charges, like that. And the electric field would still go outward through this closed surface, and the flux is still given by that expression. Let's look at our first problem. An electric field with magnitude 4 kilonewtons per coulomb is applied along the x-axis. Calculate the electric flux through a rectangular plane, 0.4 meter wide and 0.8 meter long, assuming that the plane is parallel to the YZ plane. Let's do that first. So your x-axis is that way, your y-axis is that way, and your z-axis is that way. In part A, the plane is parallel to the YZ plane, so that is YZ plane. Let's assume that is the plane that we are talking about. Electric field is applied along the x-axis, so that is the direction of the electric field. Let's assume it's a positive x-axis. The direction of the electric field is also parallel to the direction of the normal vector to that plane. The dimension of the plane, it is 0.4 meter wide and 0.8 meter in length, let's say. So the electric flux can be calculated easily It is given by the dot product of the electric field vector and the area vector. So the electric field, the magnitude is 4 kilonewton per coulomb. So that means it's 4,000 newtons per coulomb times the area. The area is 0.4 times 0.8. But don't forget, this expression is actually E times A times cosine alpha. Alpha is the angle between these two vectors. In this case, they're parallel to each other, so alpha is 0. Cosine alpha is 1. And that is the electric flux. And the answer is 1,280 newtons per coulomb meter squared. Now let's do part B. Now the plane is parallel to the xy plane. So xy plane is that. So let's take one such plane that is parallel to that xy plane like that. The normal vector to such a plane will be parallel to the z-axis. So its k hat is the normal vector to such a plane. Since the electric field is going in the direction of positive x-axis, so the electric field is parallel to I hat vector, and the area vector is parallel to k hat vector. So when you calculate the electric flux through such a plane, which is given by E dot A, you end up taking a dot product essentially of I hat and k hat. Since these two vectors are perpendicular to each other, their dot product would vanish. So the electric flux is quite simply 0. So for part B, the electric flux through such a plane is 0 Newton per coulomb meter squared. Now let's do part C. A plane contains the y-axis and its normal makes an angle of 40 degrees with the x-axis. So what that means is E dot A is the electric field, which is 4,000 that we know. The area is 0.4 times 0.8. The angle between the normal of this plane and the electric field, which is along the x-axis, is 40 degrees. So it is cosine 40 degrees, and that should give you the flux through the third plane. And calculation reveals the answer to be 980 Newton per coulomb meter squared. That solves the problem. Problem 2. A square plate of copper with 50 cm sides has no net charge and is placed in a region of uniform electric field of 100 kilonewtons per coulomb directed perpendicularly to the plate. Find the charge density of each face of the plate and the total charge on each face. So what you have is a neutral plate initially, the sides 0.5 meter, 0.5 meter, so we can calculate its area. And the electric field is penetrating perpendicularly to the plane of that plate. What this will do, it will induce charges on the surface. For example, plus charges on the front surface and negative charges at the back. So the cross-sectional view is as follows. So that is the plate. The electric field is penetrating perpendicularly to the surface of the plate, and that induces opposite charges on both surfaces of the plate. Say like that. Let's determine the total charge on each face. Let's do the right-hand side where you have the positive charges. The Gaussian surface can be drawn something like that. So the flux through that surface is given by E dot A. And that is just E times A, because the angle between the electric field and the normal vector is 0. Cosine 0 is 1. And using Gauss's law, that is just the net charge within that Gaussian surface over epsilon naught. The electric field is known to be 100 kilonewton per coulomb, so it's 100,000 newtons per coulomb. The area is 0.5 times 0.5, so 0.5 squared, equals Q over epsilon naught. Epsilon naught is 8.85 times 10 to the power minus 12. And you can determine the charge on the right-hand side. And that's going to give you 2.21 times 10 to the power minus 7 coulomb. We note this is a positive charge. Now let's do the other side where you have the negative charge. The Gaussian surface can be drawn like that. Note that the normal vector is going to the left, the electric field is going to the right. So the angle between them is 180 degrees. So let's use again the Gauss's law to determine the charge. E is 100,000 Newton per coulomb. The area is again 0.5 times 0.5. Don't forget cosine 180, that's minus 1, equals the net charge over epsilon naught, and epsilon naught is given by this number. And you can determine the value of the negative charge, which is minus 2.21 times 10 to the power minus 7 coulomb. Now we can determine their respective charge densities. Let's call it sigma. Charge density is given by the charge over the total area. So for the positive side, it's 2.21 times 10 to the power minus 7 over the area is 0.5 times 0.5, and that's going to give you positive 8.84 times 10 to the power minus 7 coulomb per meter squared. So that is the charge density on this side. On that side, it's just the negative of that number. So the charge density on this side is minus 8.84 times 10 to the power minus 7 coulomb per meter squared. That solves the problem. Problem 3. A particle with charge minus 50 nanocoulomb is placed at the center of a non-conducting spherical shell. So that is that negative charge at the center of this non-conducting spherical shell. The shell's inner radius, is 20 cm and outer radius is 28 cm. The shell carries charge with uniform density of minus 1.4 times 10 to the power minus 6 coulomb per cubic meter. So within this shell, you have a bunch of negative charges distributed uniformly. A proton moves in a circular orbit just outside of the spherical shell. Calculate the speed of the proton. So this proton will move like that under the attraction of the negative charges. If it's moving in a circular orbit, the electric force, which is given by the charge of the proton times the electric field acting on the proton, must provide the centripetal force, like that, where m is the mass of the proton, v is the speed that we are looking for, and r is the radius measured from the center of that shell. So let's calculate the electric field at that point. We can use Gauss's law to do that. The electric field at where the proton is times the Gaussian surface area. In this case, A, or the area of the Gaussian surface, is the outer surface of that non-conducting shell. The normal to such a Gaussian surface is radially outward. The electric field, on the other hand, is radially inward because we are talking about negative charges. So the angle between them is 180 degrees. So that means EA cosine 180 degrees is the net charge bounded by this Gaussian surface. The two contributions, the first one is minus 50 nanocoulomb, 10 times 10 to the power minus 9. The second contribution is the charge contained within that shell, which is calculated by taking the charge density times the volume of that shell, given by this expression. This is the density and this is the volume of the shell. And the right-hand side must be divided by epsilon naught. Cosine 180 is minus 1. We'll cancel the minus sign from the right-hand side. A is just 4 pi 0.28 squared. And E can be solved to be 15,118 Newton per coulomb. Substituting this E in here and using the charge of the proton and mass of the proton given in the problem, we can determine V. r is the outer radius, and v is 6.37 times 10 to the power 5 meter per second.